Section 3.5, regression lines. When we have a scatter plot displaying a linear relationship between two quantitative variables, the goal is to make a regression line, or a line of best fit, to model the relationship and enable us to make predictions. So a regression line is predicting the response variable y as the explanatory variable x changes. When we write it in the form y hat equals a plus bx. So y has that little kind of like caret on top. It's pronounced y hat. That's a predicted variable. X is a real variable that we'll be plugging in. And also, there's just a note here. This is really an equation in slope-intercept form, y equals mx plus b, except they're switching the order and making it y equals b plus mx, and they're using some variables that we're not used to using for that form of the equation. In this example, we have a scatter plot of 16 Ford F-150s. Along the explanatory axis, we have the miles driven, and along the response vertical axis, we have the price. We can see there's a negative association there, meaning that as the number of miles it's been driven increases, the price goes down. The regression equation, or the line of best fit, is given by this equation, y hat equals 38,257 minus 0.1629x, and we can use that equation to make predictions. So for example, we want to predict the price of a Ford that was driven 100,000 miles. So that's right about here. We can see that there's no point in that area. The prediction is going to give us the value of that point right there. All we have to do is plug in 100,000 for that x and perform the calculation. A car, an F-150 that's been driven 100,000 miles, is predicted to cost about $22,000. Let's do it again, this time predicting the price of a Ford F-150 with 300,000 miles, which is quite a lot of miles for a car. We're going to plug in 300,000 into our equation, and we see that this has a predicted price of negative $10,600, meaning that if you own this truck and you wanted to sell it, you would actually have to pay someone $10,000 just to have them come take it off your hands. Obviously, that doesn't make a lot of sense. There's a reason this happened, and it's because we're plugging in a value that's so far outside of the range of all the data points. So all our data points, these blue points in our scatter plot here, are between, it looks like 0 and a little over 150,000. Really, this red line, this line of best fit, is used to make predictions in that range. If we're predicting outside of that range, it's no longer reliable. This is called extrapolation, when we're plugging in a value that's far outside the range of the data used to make our equation. So extrapolation is something that we definitely need to be wary of, but even if we're not extrapolating, the predictions that we get from a line of best fit are unlikely to be perfect. You saw in that scatter plot that the points were pretty much none of them actually lied on the line of best fit. They were all scattered around it. So every point has something called a residual, and the residual is the difference between the actual value of y and the value of y that's being predicted by the line of best fit. Okay, it's given by this equation down here, actual minus predicted, or y minus y hat. So to give a visual representation of what a residual is, we have our line of best fit in red here. Anytime we plug in a value, like let's say we were to plug in 20,000 right around there, it's going to give us the point on the line of best fit right above that value. Okay, so we plug it in, we get a point on the line. If we wanted to find the residual, it's the difference between a point and the value predicted by that line of best fit. So in this example, it's saying we have this highlighted point right here. This Ford F-150 had 70,583 miles, and the actual price was $21,994. It's asking us to find the residual. So to start, we can plug in that x value, the number of miles. If we put it into the equation, we can see that the predicted price of this car is $26,759. That would be the value given by the line of best fit. In actuality, it only costs a little under $22,000. The residual is the actual value minus the expected value, negative $4,765. A negative residual tells us that this price cost less than predicted by the line of best fit. Our next example is about soda cans that have been vigorously shaken and whether we can decrease the amount that it'll explode by tapping on the can by so many seconds. So we can see the explanatory variable here is how long in seconds they've been tapping on the can, all right, for these different values, 0, 4, 8, and 12 seconds. They then open it up, let the can explode, and measure how much volume is left in the can. The line of best fit, the regression equation, is given by that equation right there. All right, and then it's asking us two questions, one about finding a residual and then interpreting that residual. So it wants us to find the residual for the can was tapped for 4 seconds and had 260 milliliters of soda remaining. It's highlighted in yellow here. Okay, this is the actual value of soda that's remaining. And to find a residual, we need an actual and a predicted value. Okay, we don't have a predicted value, but we can find one by plugging in this value into that equation. So we plug in a 4. We see that the line of best fit, that red line there, predicts that there would actually be 259.12 millimeters of soda left in here. Okay, that's the predicted value compared to the actual value up here. And remember, it's always actual minus predicted or actual minus expected. Okay, so the residual is 0.88 milliliters. When it comes to interpreting that residual, this soda can had 0.88 milliliters more soda remaining than the amount that was predicted by that line of best fit with a tapping time of 4 seconds. Some of the other common questions when it comes to regression lines is interpreting the y-intercept and the slope. The y-intercept gives us the predicted value when we put in a 0 for that explanatory x variable. And the slope is the amount which the predicted value of y will change each time the x increases by 1 unit. So let's put this into context of that scatter plot of the miles driven and price of the Ford F-150s. So the y-intercept is this value right here. Okay, remember it's kind of just in that flipped form of y equals mx plus b, where the b actually comes first. So that y-intercept of 38,257 is telling us the predicted price for a Ford F-150 that's been driven 0 miles. Okay, so in other words, this is the predicted price of a brand new Ford F-150. The slope, which is this other value, the one that's next to the x, is telling us how much that y predicted value is going to change each time x goes up by 1 unit. So in this case, that means that the predicted price of a Ford F-150 decreases, because it's negative, decreases by $0.1629 every time that truck is driven 1 additional mile. It's really important to include the word predicted or expected or some equivalent to that in the interpretation for both the slope and y-intercept. Because when we think about that line of best fit, that red line that went through these scatter plots, none of the points lied on that line. All right, so it's not going to give us an exact prediction. It's just going to give us in the realm, and the real life data will vary around that. So one other example with that soda scatter plot of the shaken up sodas, which gave us this regression equation right here. Interpret the slope. The slope is the one that's next to the x. It's this 2.63. And to interpret it, we would say the predicted amount of soda remaining in a can increases by 2.63 milliliters for each additional 1 second of tapping time. Moving on to the y-intercept, which is this value right here. That's telling us the predicted amount when we plug in 0 for the x. So in the context of the problem, the predicted amount of soda remaining is 248.6 milliliters if a can is tapped for 0 seconds. And just to close things out, sometimes the y-intercept isn't going to have a real world meaning because plugging in a value of 0 for x doesn't really make sense. So let's go back to this scatter plot of dash times versus long jump distance. The dash times are the times it takes to run a 40-yard dash. All right, and if we were to interpret a y-intercept for this graph, it would mean plugging in 0 for the dash time. So in other words, someone running a 40-yard dash in 0 seconds. Obviously, that's not possible. All right, so a prediction based on that value is really not a logical one.